Okay, team, we are live. Over to you, Prashant sir. The virtual stage is all yours. Guys, allow us a few seconds. Our speaker is joining us soon. He's having some network difficulties. Team, our speaker will be joining us in 2 to 3 minutes. He is having some network difficulties. Please be with us. Hi, sir.
Yes, hello. Am I audible?
Yes, sir, you're perfectly audible. You can share your screen and please start the session.
Okay. Can you make me the panelist?
Just allow me a few seconds, sir. Done, sir.
Okay, thank you. Okay, so I'm audible and visible to everyone, right?
Yes, sir.
Finally. So thank you so much, guys, for patiently waiting for this session. And I am extremely sorry for keeping you wait the last session that was scheduled for Thursday, I guess. My throat was not very okay, in fact. So I had to, take that call in the last minute. okay? Because you guys might be already aware that my sessions normally go elongated, okay? So how many of you are attending this or my session for the very first time, especially this particular project? Are you aware of what has been happening? I mean, what is the chat? Okay, so a lot of first timers are there. Okay, there was a link for the first and the second part. Sorry, I still have some cough. Okay, so lot of first timers are still there, and there are people who are new to deep learning as well. Okay. See, the scope of this session is not to get into the details of deep learning and all. I'll fairly expect that people are aware of deep learning. What are neural networks? How do you create basic neural networks? This is much on the advanced part, okay, I would say. So the first part was sort of basics, second was intermediate, and this is slightly advanced level session. Although I'll try to connect all the three sessions before I get into the deep learning and deployment part. Okay, I'll try to have a quick revision of everything. So okay, so let me just quickly share my screen and let's get started. And those who have already attended my sessions, they know that I do not have PPTs. So all I have is this. Let me just quickly share my screen. So you can download all the code from GitHub. I have uploaded and updated all the previous codes. So let me share that link with you. Okay, the GitHub link for the data today. So this is the GitHub link. Okay, so you guys should be able to download. So part 1, part 2, and part 3. I have updated all three. Okay, I have updated all the three parts. Right? So I've updated all the three parts, and I did take some word embeddings also. So that introductory file is also there. And I was facing some challenges with the GPU. Last time, as I already mentioned, that I was using a cloud-based GPU. So I've got all that sorted. And today's session, again, I'll be continuing in that GPU itself. And of course, the reason being the model trainings for the deep learning ones, they will take a lot of time. So I just want to save all that. For that reason, I'll be running all of my codes in a GPU-based environment. You can very well download it and run them locally. Okay. So all the outputs are there. So even if you're not able to run it, that's still very fine. Okay. So I would not have much to add. Whatever technically I have to discuss, I've already updated in these codes. Okay. So this link, I'm sharing it once again. The moderator, please keep a track of this. So henceforth, if anyone is asking, so you can pin this comment. I don't know if that is possible here, but yeah, fine. Okay, so here I come, and I have uploaded all those 3-4 files. So I'll start with this. And what I have done is just to give a quick overview for the people who are completely new and joining today. So these are the 13 steps, in fact. 13 step I just forgot. That is fact 12. Let's CNN. So these are the 12 things that I have discussed in the last 2 sessions. In fact, 2 sessions I finished somewhere here. And today's session is mostly going to be focused on this. Okay, but this will take the last half an hour. So just to half an hour, not half an hour, in fact, slightly, you can say 40 minutes. So the first 40 minutes, I would be again slightly not discussing, in fact, I would be giving a complete walkthrough of what all has been discussed. I'll not go ahead and explain any of the terms here. Okay, for that, you can very well follow the previous videos. We have discussed enough in detail. And the reason I have to discuss about this, the previous steps that have already been done is so that people who are attending today, in fact, who are new, or even if you have attended the previous 2 sessions, you will get a connect. This is all what we have done, and this is what has been tried, and these are the results, and this is what I'm expecting next. Okay, so just to get with that context and connect, I'll still have to go through everything. Okay, so what I have opened here is the very first file. This is my sentiment analysis part 1. Okay, so part 1 is this file. Okay, so that was taken in the very first session. So tweets data was loaded. You can see this is the tweets about some mobile phones. So tweet data set loaded. We did some basic data visualization, cleaning, in which we removed the hyperlinks, URLs. Okay, we focused only on the text, all the numbers, punctuations, smileys, @ user mentions, everything got deleted, and we converted that into a cleaner function, which we applied. We applied that cleaner function, and finally, my clean data set looks like this. So you can see here. Okay, so you can see here, these are the raw tweets, and this is after I apply my cleaner function. Okay, that cleaner function I have discussed. And then we visualized, okay, what are the top 25 terms in the cleaned tweets. So this is the raw tweets. You can see not much informative. Okay, you can see some text like to my, these are mostly stop words. And after we cleaned by using the stop words, okay, and other things, you can see the @ signs, the hashtags, user mentions, okay, .. .com, these kind of words are gone. Okay, so you'll see more informative words coming, and after applying the stop words, even more informative words would be coming. Okay, now you can see. So that was the data visualization part. Next, we went ahead and did a bag of words model. This is basically a technique to extract features out of your text. Textual data is completely unstructured because each tweet you can see. Okay, so I have now 3 columns. This is my raw tweet, as you see. This is the tweet without the stop word removed, and this is the same clean tweet, okay, with stop word removed. Okay, so for the purpose of modeling, I'll be using the second column, okay, which have the stop words, and we'll try to remove the stop words by using bag of words model like count, vectorizer, TF-IDF. That's all the trials we have done in the previous 2 sessions. Okay, so the second column is what I'll be going throughout the session. Okay, fine. So these are the 2 techniques which I have tried. One is count vectorizer and one is TF-IDF. The purpose of this vectorizer function is to basically convert your unstructured data. Why is it unstructured? Because each tweet will have a different word length, different character lengths. Okay, what I want is I want to extract features out of this tweet. Okay, such that every single tweet must have the same number of features. That is what we call as structured data. So each row must represent 1 tweet, and each column will be 1 feature. So that kind of thing we do not have. Okay, so that is what the purpose of feature extraction using bag of words model is. Okay, so there are 2 strategies that we have tried. One is count vectorizer, one is TF-IDF. So in the first session I have tried count vectorizer. Second session I did the TF-IDF. I even explained the calculations. Okay, so please go through those videos, and you can see after I do a transformation, fit transform, this is the kind of data that I'm getting. So this is the structured data basically. Okay, so 7,920 tweets, and each tweet has got 15,955 features. Okay, fine. Someone is saying, Gulzar, screen share is cutting. I absolutely know that. I have zoomed in so that you focus only on the relevant part. Okay, only when I zoom out, you will be able to see everything, but with you would not be able to make out anything because the font size is just too small. Okay? So I'm just zooming in for the relevant part. Okay, so don't worry on that. Perfect. Okay, so you can see this is how unstructured data got structured. I have got 7,920 data points. Basically, each data point is nothing but a tweet, and 15,955 features. So what are these features? Basically, the bag of word model will give you individual words as the feature. So what we created is a bag of words, also called as the vocabulary, in which we have the collection of all the unique words from those 7,920 tweets. Once again, I repeat, 15,955 is the number of unique words in these number of tweets. So each word is now being considered as a feature. Okay. So, and then what we did is sort of a one hot encoding. That's the reason you will see so many number of zeros and ones. Okay, mostly zeros. And these are the features we were able to extract. I'm just printing the top 50 features, you can see, in alphabetical order. Okay. And you can see these are 15,955 features. Then using those features, we went ahead and made a logistic regression model. And since the data set is not perfectly balanced, you have a 40-60 ratio, I think. Sorry, no, 75-35, 75-25 ratio. Somewhere we had printed. That bar chart was there, so you can see. So it's like 3/4 and 1/4. Okay. I think, yeah, 3/4 and 1/4. So 75% data set has a label 0 and 25% data set has got a label 1. So it's not perfectly balanced. For that reason, I'm using the class weight option from logistic regression. Okay, you can study more about that class weight option. Okay, so this tends to handle the minority class also. And then some solver I'm using, and I'm using a L1 penalty. And the reason for using the L1 penalty is I have roughly 16,000 features. So L1 is your lasso regression, and lasso has a built-in feature selection capability. So basically it will try to reduce the model coefficients to almost 0 for those features which are not very important to the model. That way, directly, the important features get selected because their coefficients would be non-zero. Okay, the useless features will have 0 coefficients. That is kind of L1 penalty I'm using. And by some trial and error, I figured out 0.4 is good. You can check out the very first session where I have actually done this trial and error during this session itself. Okay, so from that 0.4 I have got, and I'm going to continue the same 0.4 and L1 penalty and the same solver and the same class weight option throughout. Okay, for all the analyses. So this is the training and test results that I have got. Okay, initially without using the penalty, you can see, without using the penalty, this gave me an overfitted model, 98% in the training set and 88% in the test set. That much difference clearly shows a overfitted model. Okay, you can see the training score is 98% roughly and 88%. So 10% difference is not acceptable. So that is the power of regularization. So you did a regularization and now you are getting 90% in the training set, 88% in the test set. Perfect. Further, we wanted to do a cross validation. So these are the 5-fold cross validation accuracies. And this is the mean cross validation accuracy you have got. And this is the standard deviation. So essentially, what you're trying to say is your model's performance is 88 point something percent plus minus 0.93%. So that is the standard deviation you can expect from this model, which is very good. In fact, I would say as long as the standard deviation is less than 1%, it's very reliable model. Okay, good. So, and then we try to do a hyperparameter tuning. So the hyperparameter that we try to tune was C itself. So for people who are not satisfied with that C of 0.4, we did some hyperparameter tuning and all that results I'll not discuss. That's all discussed in the very first session. So I'll just skip this part. But hyperparameter tuning was also done using a pipeline. So in the pipeline, two things are happening. One is your count vectorizer. Two things are happening in that pipeline. I'll just show that pipeline first. Okay, it's there later. Okay, so this pipeline. Okay, So vectorizer followed by your estimator. So that is a pipeline which I am, fitting kind of. Okay. So now for further experimentations, okay, I created this pipeline, and every time I'm going to fit this pipeline. Not just fit, I'm going to cross-validate that pipeline. Okay, so that is what I have done. Fine. We also created this logistic regression model after removing the stop words. So right now this X have the stop words. Okay. So now I wanted to see if removing the stop words made any difference. So you can see the after you remove the stop words, okay, the accuracy actually came down from 88% to 86%. So possibly for this data set, stop word was important. And one reason I believe could be that there are words like not, negation words. So this feature is not satisfactory. Now not is a stop word. If you remove that, okay, the label changes. This feature is satisfactory. Okay, I'm not happy with this particular feature not working. Now if you remove that both the nots, I'm happy because this feature is working. I mean completely, the sentiment changes because of that negation word. Okay, so I have not personally handled or have not customized the stop words to handle the negation words. So if you want, you can remove the negation words from the stop word list, and then you can apply and see if there is a difference. So this is one reason I believe, because of which after removing the stop words, the accuracy of the model has gone down. There could be some of those negation words or some of those words from the stop word list which are probably important. So how many words did you remove? You can say that was 955. This is 673. Roughly 300 words you have removed. 255 to be precise. Okay. So in 955 minus, see that many words were removed. 282 words were removed. But there was a loss of roughly 2% accuracy. That is huge. So this 282 is nothing in front of 15,000. So the percentage reduction would be hardly anything. You see, the percentage reduction, if you want, that would be that by this number. So after removal, the percentage reduction is only 1.76%, and that reduction somehow influenced my model's performance. Perfect. So same thing. Okay. So here what I did is additional thing. After removing the stop words, I'm also applying the minimum document frequency. Okay. So what it essentially says is I'm going to build the features from only those words which are appearing in minimum 10 documents. Okay. So basically in your vocabulary, now you are going to retain only those many words which have at least a document frequency of 10, or those words which appear at least in 10 documents, right? And still that number might be 2000, 3000 or something. You can see that number is roughly 1086 with minimum document frequency of 10. Okay. So still I have got 1086 features. Now I still want to further narrow down. I'll select the top 300 features out of it. Okay. So you can see the accuracy of the model has further reduced to 85%. So 86% with stop words and the minimum document frequency. So with the stop words, it reduced to how many? 15,673. When you apply the minimum document frequency of 10, those 15,000 reduced to only 1,086 features. And then you say, no, I don't want even 1,086 features. I want only top 300 features. Why 300? We will discuss that. And then the model accuracy further dropped to 85%. Okay, so this is the number you have to keep in mind. Okay, this is the performance of a bag of words model with 300 features. Perfect. The same thing was repeated using TF-IDF, so I'll just skip this part. Okay, and then we did a dimensionality reduction. So PCA will fail. That was also mentioned and shown in the last couple of sessions. So PCA will fail. PCA does not take sparse input. The output of count vectorizer and TF-IDF, they are sparse. So PCA will fail. For that reason, we are using the truncated SVD for dimensionality reduction. Okay, and here I'm using 1000 components. You can even go for 300 components. So 1000 components, and you see that this is the performance. Okay, this is very much comparable. I would say this is very much comparable to this result where you had 1086. So 86%, and this is also giving you a similar 85, slightly lower in fact. With the same number of features, roughly you are getting a poorer performance in dimensionality reduction, which is very much expected. And you see, this is the test accuracy 85.24 with 1000 features. Okay, now why is that? Because dimensionality reduction by truncated SVD or PCA or any other technique, they are unsupervised techniques. So when you are applying an unsupervised technique for a supervised problem, that will mess up your data to some extent. Okay, so the class information is not used while doing the dimensionality reduction. I hope you agree with me, right? The class information is never used, which is why the objective of the dimensionality reducer is only to capture the variance in the data set and not the class separability. And for that reason, it is very much expected that the test accuracy will reduce. So after applying the dimensionality reduction, you are getting slightly lower accuracy. Fine. This was done in the last session, that is part 2. Okay, the Engram model. So we did Unigram model in the very first session, and then we tried bigram and trigrams also. Okay, so this was the same code. I'm not going to go through the code, but somehow this plot was not appearing. So this I got sorted, and I have uploaded the updated notebook. Okay, so this is how it looks. So what I have plotted is basically the top 25. I've plotted the top 25 features with respect to their coefficients, the top 25 features which have the highest positive and the highest negative coefficients. So positive coefficients would mean a negative sentiment here, it's the other way around, and negative coefficients would mean a positive sentiment here. Okay, so it's other way around because I have already mentioned the class labels. Okay, 0 is positive and 1 is negative. Okay, so I'll show you there. Yeah, it's clearly written. 0 is positive and 1 is negative. So it's actually the other way around. Okay, so the words which have negative coefficients, they are actually more important to the positive sentiments. They are reflecting a positive sentiment, whereas those words which have a positive coefficient, they reflect a negative sentiment somehow. You can see very well. Okay, those blue words. Okay, I don't want to spell out, but you can see suck, blast, whatever you can see. Whereas these words like cute, beautiful, food, girl, birthday, gaining, happy, you can see happy, so on, right? You get the point. Now, after some tweak, okay, I was able to extract Biogram features also. So I did train the model using unigram and bigram. How do I mention that unigram and bigram? You can see it here. So count vectorizer, this is Engram range 1, 2. So this is where you are specifying I want unigram and bigrams both. Okay, unigram. So 2 means bigrams, and minimum document frequency of 5. So obviously the total number of features will increase, right? So initially it was 1086 or something 2000. Now it has increased to 3322 basically because of the bigram features as well. And if you want, you can look at the bigram features also. Let me. I think I'll show it from here itself. So you can look at these bigram features, Apple, Mac, IO, Apple. So can you see these are all 2 words? These are bigram features. These are all 2 words. Okay. Now this is the result of L1. So because of that, some of the model coefficients are very, very small. Can you see the gap here in the plot? This gap here in the plot shows that these features have very, very small coefficients. These features have very small coefficients. It's not even appearing in the plot. Okay. If you had used the L1 regression, I can show you the plot, how it looks if you had used L2. Sorry. If you had used L2, L2 is ridge. Okay. L1 is lasso. Okay. Lasso is very merciless. It will simply bring down the coefficient to 0 if that feature is not important. It's that merciless. So I'll just show you those plots. How does it come up? So you can see those bigram. So these are the bigram features. Okay, after using L2. In the current code, I'm using L1, but I also tried a parallel code where I used L2. So then you can see these Biogram features having some decent coefficients, so they are visible here. Okay, perfect. How about Trigram features? So again, so this piece of code, you can see this part, Engram range. So I have unigram, bigram, and trigram, all three, one by one. Okay, and then some tweaking into the code, I am able to extract the trigram features, the top 25 trigram features, and you can see only one bar. Again, the same reason I said. The other ones have very small coefficient compared to this last guy. Okay, that is the reason they are not even appearing. Whereas if I had used L2, I'm able to see the trigram features. Can you see the trigram features? So those bars are now visible because this is L2. And still in L2 case, there are some trigram features which have very, very small coefficient. What does the small coefficient practically mean? Small coefficients practically mean that they're not very important to the model. It is as simple as that. Fine. Fine. So that was the part one. In the part two, if you saw that last part of the part one, I pickled my data set so that I don't have to repeat all the same process to get the same data set for the next notebook, right? I'll be simply reading this pickle file or import the pickle file. Okay, fine. So that is what I have done in the very first block in the second part. Okay, so reading the pickle file and everything else is same. So continuing, we did the word embeddings. So primer on the word embeddings is already done in the previous session. I'm not going to repeat, but we did the word embeddings by two approaches. Okay, one, by training our own custom word-to-vec model. Okay, so when I did a custom word-to-vec model with 300 vector size, okay, so you can see the vector dimensions is 300 here. And for the entire data set, so what we did was basically converted our tweets into a list of lists. Once again, I repeat, I converted all the tweets into a list of lists. Okay, your entire series, one column of a data frame would be series, correct? This one column is a series. So I'm converting that series into a list where each tweet itself will be a list of tokens. Can you see I printed the first tweet? The first tweet itself is a list of tokens. So that is the kind of input the word embedding models expect, right? So Gensim is the package. You can do a pip install. I've already got my environment sorted. So this all code works. I'm not going to run this right now. So I trained a word-to-vec model, and this is a CBOW model. So that was also discussed in the last session. There are two types of word-to-vec models. One is continuous bag of words. One is skipgram. Okay. So how do I know? The skipgram is 0. So if the skipgram is 0, then you know it's a CBOW model. Okay. So I printed my CBOW model. Okay. I printed. There is a question here. What is the use of Lambda function? Lambda function is to Lambda functions are anonymous functions. If you want to create some functionality and apply then and there, you don't want to save that functionality for later use. For that reason, you are using the Lambda functions. So Lambda functions is like you are creating a function in line for using or for doing some data manipulation. In the same line, you are using it. So in one line, you are not only creating that function, but also using or applying that function. Okay, so that is why Lambda functions are also called as inline functions. Now, since they are not being saved, they are also called as anonymous functions. So they are single use functions. So what is this function taking? This function is taking one tweet. X is what? X will be one tweet. X dot split. What does this Lambda function return? It returns a list of tokens. This is the kind of list it will return for each tweet. Simple. Right? Okay, so my word-to-vec model was able to identify 2,420 unique words. I have mentioned the minimum word count to be 5. So consider only those words which have a frequency of 5 or which occur in 5 documents. Think it that way. Okay, word frequency here doesn't mean the absolute frequency. It means your document frequency ultimately. and there's a window size. So all that options we have discussed. So now what two-way model was able to identify 2,420 unique words from my 15,955 initially that we got from the bag of words. So out of that, this model was able to figure out 2,420. Okay, these are the most important features. And each word was assigned a vector of 1 cross 300. So basically, I am converting each word into a dense vector, Basically, what is a vector? Vector is nothing but a collection of numbers. So now I am going to represent every word of my vocabulary by a vector. Okay. So that is called as word vector. Fine. So I think I've already mentioned about all that. So this is how you can see the word vectors coming down. For example, word vector for this word is, so this is the bunch of numbers which are representing this word now. This bunch of numbers are going to represent this word. So similarly for each word, so this word sentence, this is the word vector. This is the word vector. Is, this is the word vector. This, okay, this is the word vector, and so on. Okay, so that you can define. So that is what we did. So I created my own custom word-to-vec model. So this is your CBOW model, and these are the words in your vocabulary. Perfect. I have got 2,420 words in my vocabulary, and each document now will be converted into 1 cross 300 by using these word vectors. Okay. So this was a custom function written to convert the word vectors into document vectors. That also we have discussed in the previous session, so I'm not going to discuss this. So now after converting my word vectors into document vectors, now each document vector is like this. Can you see? Each document vector is a collection of 1 cross 300. It's a collection of numbers. So this is one tweet. Essentially, this is the tweet number 1. This is your tweet number 2. This is your tweet number 3. So these are called as document vectors, but these are the vectorized tweets. Fine. You can very easily see that each document vector is 300 dimensional. Okay. Now I'm going to dump all that into another temporary data frame and finally convert everything into a NumPy array. So that NumPy array is of this size. Okay. So this is your final feature matrix, which I'm going to use for building a word embedding model, you can say. Okay. So 7,900 tweet, and each tweet is a bunch of 300 numbers, exactly like this, right? Each tweet is a bunch of 300 numbers. Perfect. So that is the final data frame model, you can see. Not data frame, but a NumPy array. Now that NumPy array is dumped into a data frame just for easy visualization. You can see these are the features. These are my features. These are my features. Okay. So likewise, you will have 300 features because 300 dimensional data we are, 300 dimensional vector we are using. Okay. So shape of the data frame is 7,920 because that was the exact number of tweets. And one additional because I am also appending Y at the end of my data frame. Can you see? Y is also there at the end of the data frame, right? Because of that Y column, okay, it is having one. Fine. So now I have got my X and Y separated out of that data frame and usual imports, okay. Logistic regression, cross-validation, stratified, threefold, scaling, and all that same. I'm going to use that word embeddings as the input. Pipeline. So I'm creating a word embedding pipeline. So within that pipeline, what am I doing? I am first scaling my data set, although that's not mandatory, but you can try doing this and without this, both. You can try both the versions. Okay. So what I have done is this data frame was scaled. I ran a standard scaler. For each feature, you can see. So the first step is standardizing your features. The first step in the pipeline is standardizing your features, and those standardized features will go for model building, the same logistic regression model, right? And that was cross-validated. These are my results. Okay, so 85% accuracy I'm getting on my own word embedding model, right? I'll show you something interesting. that. Okay, so what I did was, if you go to skipgram 1, okay, right now I have used skipgram 0, okay. If I make it 1, can you see? This was originally 0, I made it 1. So essentially what you get is a skipgram model now. And you rerun those steps. When you rerun those steps, okay, by changing it to 1, okay, I get a higher accuracy. Maybe I can show you. So that was 85, 86%. Let's see how much this gives. I'm just zooming it out and running. Okay, I'll have to start from start once again, it seems. So it's training. So I'm not changing the names. Okay, everything else is same. Okay, running it quickly. Let's see what. So can you see now I'm getting 87%. Originally it was 86%. Did you notice? I've got a higher accuracy with the skipgram. This is the result with skipgram model. Okay. Initially with the CBOW model, continuous bag of words model, I was getting roughly 85 to 86%, right? I was getting roughly 85 to 86%. But now I'm getting roughly 87%. But definitely that's a much better result. So one of the story here is you should try out every possible thing. No one can guess which will give you a better accuracy. Don't ask me such questions. Okay, these are all hyperparameters. Okay, which kind of model or which parameter, which hyperparameter will give you a better result? I mean, I have taken 300. You can experiment with 400. You can experiment with 200. You can experiment with 500. You might get still a higher accuracy than this. Okay, so why did I take 300? That is pretty standard. 200, 300 is a standard. Okay. And another reason is I wanted to compare it with a pre-trained model like GLOVE. So what I did is further imported the pre-trained model like GLOVE model and slightly tweaked that function. Okay. And I'm getting the word vectors from the GLOVE model now. So if you remember that GLOVE model, I had given you the link. Okay. 600. This was the file name. Somewhere it is mentioned. Okay. So you can download that GLOVE model from here. Okay. This link. You will do all the links, and you can even do a Kaggle search also. So Kaggle also you will get that link. Okay, to download that 300 dimensional vectors. Google use negative bin something like that. Okay. Sorry, am I audible? Yeah, connection got lost. I think. Yeah. There was some problem with the connection. That's why it asked me to. Fine. So Google News, negative, Ben Kaggle, just search something like this. You'll be able to download all that data set. Okay, that also was mentioned. Okay. Anyway, so I'll continue. Maybe you can just figure that out. All that links are there. Okay, so you'll be able to get that. Fine.
Sir, sorry to interrupt. Your screen is not visible.
I did share my screen. So now is it visible?
No, sir.
Okay. Am I visible?
No, sir, your video feed is not visible as well.
Nothing. I just now is the screen share visible? I just shared my screen once again. Your screen is loading. Okay. No, hasn't still been updated. Just a minute. No problem. Yes. Is it a Zoom problem? You guys can hear me, right?
We can hear you, sir, but it's breaking too much.
Okay, I'll just change my network then. Okay. Just
Sure,
a
sir.
minute. Okay. Now my screen share is visible.
Yes, sir, your screen is visible now.
Okay, perfect. Thank you. Thank you. Yeah. So this link you can download. Maybe if you want, I can put this. Okay. Okay. So this was there. So you can download this. It's a 3.6 GB file. It's a 3.6 GB file, and this file was processed. How was that processed? I'll just show you. This file, which is also shared in the GitHub, it was processed by using this code. Let me show you. Okay, I am not going to run this. This file was processed 6B. So you can download this. You can download this zip file, and within that you will get 50 Ds, 100D, 200D, and 300 Ds. So once you process that, you'll get a Word2Vec file, and I'm going to only use that Word2Vec file. Okay. So this file is what I'm going to use in this notebook. So this notebook only is using that. Okay, I'll just show you. Only I'm using that. I'm just importing and just fetching the word vectors, and using those word vectors, I'm just training my model. That's it. So it's no training with respect to creating new word vectors. So I'm not creating any word vector. I'm just importing the pre-trained word vectors from the GloVe model. Once again, I repeat, I'm only importing the pre-trained word vectors from the GloVe model. Okay. So the pre-trained GloVe model vectors are exported into that text file, Word2Vec text file. Okay. And I'm just importing all those word vectors. Don't try to open this. This will be a GB file. So your notepad will hang. So don't try to open that. I'm just importing all my word vectors by using this function and this for loop. Okay, this for loop is being used, okay, to fetch all the word vectors from there. Okay, fine. So there's a small change here. Should be this one. Save this. Fine, and then the accuracy of the model. Okay, so the word embeddings were obtained from the GloVe model. Word embeddings were obtained from the GloVe model, and now you can see very similar accuracy. So see, the advantage of this is you don't have to train your own custom word embedding model. This is what you are already taking from a pre-trained model. So you can either use the Google News, which is a huge file, or you can go for GloVe model 6B zip file, in which you have option of using 25, 50, 100, 200, and 300. So there are 4 files, 4 text files in that zip. Use one of them. Okay. So all that we have discussed in the last session. So just go through that video. Fine. So that is where this stops. I said 40 minutes, but I took 40 minutes because I started the session 6 minutes late. So perfect. We are bang on time. Okay, so now the next and the last part is the third part, where we are going to actually create these word embeddings from a deep learning model. In fact, the GloVe model, the CBOW model, the Skipgram model, they are already deep learning models. They are already deep learning models. So that Skipgram model and the CBOW model, they are actually single layer neural networks. Okay. In fact, 2 layers, because one would be a hidden layer, okay, and one would be your output layer. So it's a 2-layer network, you can say, definitely. Okay. So they are actually very simple. So CBOW and SkipGram, they are already deep learning. So we, although are saying that we are going to do NLP using deep learning today, but we actually did that in the last session itself. But what additional are we going to try now? Okay, that's the point. So we have done word embeddings from our own custom. Okay, so you can say train our own word embeddings model. That's what we did. We tried both word to vec as well as CBOW. Okay, SkipGram as well as CBOW both. And then we did the word embeddings from the glove model. So that was the last part of the part 2. Okay. Now this is the thing that we are going to try out. Okay. So first we'll create a simple neural network model without word embeddings. Let's see what is the performance. And then if we have word embeddings, okay, how to learn the pattern in the word embeddings. For that you will need some feature extraction, like feature extraction layers like CNN layers. Okay, and then we'll create a deep learning model. So that is the whole objective. So before I venture into that, let me see if there are any questions. Okay, so I have very old students also. Sumit, thank you. Okay. So I'm looking at the Q&A section. If there is anything that I can discuss right now. Not yet. Okay. So maybe those two questions we'll discuss in the end. They are not immediately relevant. Okay. Perfect. So any questions on the YouTube side, the moderator? Ritik?
No, sir, not as of now.
All good, all good. Fine. So now I'll just load the data set. It's the same thing. Okay. And I've already mentioned that 0 refers to the positive sentiment, 1 refers to the negative sentiment. Fine. So we'll first create a simple deep learning model, okay, with binary features. Okay, with binary features. What are binary features? So basically, again, you will create a vocabulary containing again those 15,000, 16,000 words. Okay. You will be using each of those words as features. Okay. So essentially, it turns out to be a the feature part will turn out to be a bag of words model. You can very well use the output. Listen to me carefully. You can very well use the output of the count vectorizer, convert that into a dense, and you can feed that output of the count vectorizer to your deep learning model. Right. So even that can be tried. Right now, I'm doing everything using TensorFlow, functions basically. Okay, I'll be using the TensorFlow or the Keras functions to do the same thing. What count vectorizer is doing. So this is, a deep learning way of doing the same thing. There are a lot of similar functions you will find, okay, in the utilities part, okay. Fine. So this binary model is exactly a bag of words model. Let me repeat that once again. It's just marking the presence of a word from the vocabulary if it is present in a given document, in a given tweet right now, right? If a word is present in the vocabulary and now also present in your tweet, then it will be marked as 1, otherwise 0. That's the kind of binary model we are discussing. Right? Perfect. What's okay? Share the screen. Okay, perfect. So here onwards, I'll be a bit slow and discuss everything line by line. Okay. So I have written a function, a simple function, which will return a deep learning model. It is as simple as that. Okay. So in Keras, I'm going to use Keras. You can see. So what is Keras? Keras is a wrapper over TensorFlow or Theano. I mean, it's a wrapper. So the framework that I'm using is TensorFlow. Basically, behind the scenes, I'm going to use TensorFlow. So what is framework? Framework is, a library, you can say, which can be used to create neural networks from scratch. So what are the frameworks available? TensorFlow is one framework. You can literally create any kind of neural network using TensorFlow. Second is Piano, Cafe, and then you have Fast Fast AI, and many other frameworks are PyTorch. PyTorch, one of the most important competitors of TensorFlow is PyTorch. So industry uses one of these two. I mean, 95% of the industry, I would very safely say, or maybe even higher, either uses TensorFlow framework or uses PyTorch, right? Either uses TensorFlow or uses PyTorch. Now, TensorFlow codes are very lengthy, and that's the reason you need Keras. So Keras is a wrapper over TensorFlow. So one line of Keras behind the scenes is equivalent to 20 lines of TensorFlow code. So that is why people prefer to use Keras, because that's a wrapper. So creating and running, compiling, summarizing the models are very easy in Keras. But if you try to do the same thing in using low-level API functions from TensorFlow, that will take huge amount of code. So not really suggested for beginners at least. Okay, that is one. Second thing is. Okay, so in Keras, if you go to keras.io, that's the documentation page. So there are two ways you can create deep learning models. Okay, go to the API doc. There are two ways. One is called as the sequential API, and one is the functional. Okay, so where do you get that? A lot of things are here. So I would say go to the getting started. Should be able to get it. Not here. Yeah, this one. So one is the sequential class. That is what I am going to use right now to create my models. So one is the sequential class, and the other is functional API. Okay, the other is the functional API. If you just click on the sequential class. So what is the sequential class? Basically, it helps us to create a deep learning model where you have a sequence of neural network layers where the data flows from left to right. That's it. There is no branching, there is no merging. So as long as there is no branching and merging, you can very easily create such networks using sequential class. The other is the functional API where you can have various branching and merging. Okay, so maybe I can show you how does. So can you see this? So data goes from top, comes out at the bottom. That's it. So your features are fed. So this is your deep learning model. You can say the features are fed here, and the output is coming from here. That's it. This output would be just one. Can you see? This is either going to be 0 or it is going to be 1. Basically, it's the output level. So you have just one neuron in the output layer, okay, and you'll have multiple things going on in the input layer. So your input comes out from here. So that data is processed, further processed, further processed. So each of these hidden layers are processing your data, right? So these are the 3 hidden layers I'm going to use. Okay, and there is one output layer. One output layer. This is your output layer, right? So it is as simple as that. There is no branching and merging. So if you want to do the branching and merging, you better go with the functional API. Okay, so if you just search here functional API, get that functional API. And I want to purposefully show that, see, this is not a session on deep learning. I have mentioned that very clearly at the start. Okay, so some familiarity with deep learning is already expected. The thing is coming up here. Somewhere here. Functional API should be there. The reason I want to show you is you will get a clear idea. Okay, or you use the model class, basically. That itself is a type of your functional API. Okay. So is there a output displayed? No. Problem is this itself keeps on changing so much it becomes difficult. No. Earlier they used to have one page on functional API where they had given a very clear differentiation when to use sequential and when to use functional. Anyway, so we'll skip that. So as long as your data is not merging into multiple, networks. So imagine that another parallel network is there, another parallel network. And so whatever your input is, this is your final input. Let's say this is your input. So input is being fed to two networks parallelly. Goes here as well as it goes here. Now here a different set of processing is happening. Here another set of processing is happening. And then finally you merge both of them. So there is a concatenation layer and then it goes to your output layer. If this kind of network you want to create, this is typically used in GANs, autoencoders, especially, and because you have a encoder network, you have a separate decoder network. And so all this branching and merging, okay, can be done not by sequential class, by using the model class, the functional API. So here we are not going to create any of these exotic neural networks. We are only going to create a very simple neural network where the data flows left to right or top to bottom. That's it. Okay. So here you have the input layers. So just imagine you have the input layers. You have few hidden layer neurons, and here you have the output layer. That's it. And then you have the connection between all of them. So basically, so I would just say this is my input layer. This is my hidden layer HL1. This is my HL2 hidden layer 2, and this is my output layer. That's it. That's it. Okay. And then these are all connected. So that is the kind of network we are creating here. The input layer has got 15,351 nodes. These are nodes. Okay, these are nodes. These are not neurons. Whereas these are neurons. Okay, these are the neurons. These are the neurons. So neurons are those which processes your data. Input layer nodes do not process the data. So how many nodes you are creating in the input layer? 15,351 nodes you are creating. Why 15,351? Because that is the number of features you have in your data set. So how do I know how many nodes will be needed? The number of nodes in the input layer will be equal to the number of features in your data set. Now, why 15,351 features? Because that is the number of unique words in your vocabulary. So that is the size of your vocabulary, right? That is the vocabulary we have been using all now. Okay. Now, the first hidden layer, you can see, contains 64 neurons. So this contains 64 neurons. The next hidden layer contains 32 neurons. You can see these numbers. And the last hidden layer, the last layer, which is my output layer, contains a single neuron. Is that clear? This is the neural network I have created for you. Yeah, this is the neural network I have created for you. Fine. So the input layer contains nodes. Nodes do not process the data. They are only there to collect the input from your data set. That's it. It collects that input and passes to the neurons of the hidden layer, okay, which actually does some computations. What kind of computation? I'll show that. Okay, that is defined in your activation function. We are going to use ReLU as the activation function, that is rectified linear unit. And so the hidden layers use ReLU. Both the hidden layers use ReLU, and the output layer is going to use the sigmoid activation function, right? So why sigmoid? Again, because the output has to be as a probability in the range of 0 to 1, and that probability will have a threshold of 0.5 default. So I want one output, whether it is 0 or 1. That is basically the class label. When you want to have multiple outputs, you need multiple neurons in the output layer, and then you would be using something like sigmoid, okay, instead of softmax instead of sigmoid. then you would be using softmax instead of sigmoid. So right now I'm using sigmoid. And here in the hidden layers, I'm using rectified linear unit, really. Okay. So this is the neural network architecture that I'm going to use. 15,351 nodes in the input layer. Once again, 64 nodes in the first hidden layer, 32 nodes in the second hidden layer, and the last layer is your dense layer again, which is your output layer, right? So if you have some background about deep learning, this much is more than sufficient to help you understand what am I doing. Okay. Okay. So these are the codes. So 64 neurons. Input shape is basically the total number of words in your vocabulary. You can see, and I mentioned that some activation function is needed. That is basically what computation or what kind of calculation or what kind of transformation you are doing with your input features. So that is dictated by your activation function. Okay, so this activation function is needed to do some computation on your inputs. Fine. And then some regularization, built-in regularization I'm using. Here you can again use L1, L2, and then again further you can define your parental parameter and so on. Right. If you want, you can again, if you fear that there is this deep learning model can overfit. If you fear that this deep learning model is overfitting, you can uncomment the dropout layers. So what the dropout layer is going to do is 25% of the inputs from this layer is not going to go to the next layer. Once again, I repeat, 25% of the neurons in the previous layer will not be able to give their outputs to the next layer. Which is the next layer? This layer. So what I'm saying is randomly drop the output of 25% neurons of the previous layer. Why do I want to drop the outputs? To prevent overfitting. So maybe later on we can discuss in detail how does the output dropout layer work and all. But a single line answer when to use dropout. It is always supposed to be used between two dense layers, number one, and the purpose of using is to prevent overfitting. So if you still fear, you have already used regularizer, but if you still fear that there might be some overfitting, you can use the dropout also. One last point about dropout is dropout layers do not have parameters. Okay, the input layer has got parameters that will add huge number of parameters as you will see from the model summary. Okay, so model parameters is what is learned during the backpropagation step. So you are going to train your neural network. So backpropagation algorithm, some optimizer function we are going to use. Can you see here? So the output layer is right now using sigmoid. Binary cross entropy is the loss function we are going to minimize. So what are the available? Go to the API reference. Okay, so these are the activation functions available. These are the normalization layers or normalizations possible. These are the optimizers. These are the metrics. These are the loss functions. Okay, let me show you one by one. So these are all the different loss functions available. Right now, I am using binary cross entropy because I'm solving a classification problem. So I'm using a binary cross entropy loss. Okay, in my code, I'm using a binary cross entropy. If you have multiple labels, more than two, it's a multi-class. Let's say 5 labels, 10 labels. For a multi-class problem, you will use categorical cross entropy. Don't experiment with a number of things. Very, very clearly. For regression problems, use MSE. It is as simple as that. Okay, MSE, mean squared error. That is as simple as that. Once again, I repeat, if you're solving a regression problem, use mean squared error. That's it. If you're solving a binary classification, go for binary cross entropy. And if you're solving a multi-class classification problem, directly go with a categorical cross entropy. That's it. Don't spend time in experimenting, at least not when you are learning the stuff, basic stuff. Okay. You can try out others, like KL divergence is not used for supervised learning. That is normally used for unsupervised learning. Normally, again, in auto encoders, okay, GANs, where you want to find out the difference between two probability distributions. Okay, so that is where you would be using the KL divergence and all. Fine. So this is all about the loss functions. So what loss function is this going to minimize? Then who is going to minimize? That is where the optimizers come in. Okay, so which algorithm is going to find the minimum value of the loss function? Okay. And why do I want to find the minimum value of the loss function? Because once you obtain the minimum value of the loss function, those parameter weights, these parameters, which I'm going to print. Okay, so these parameters, can you see on this here? So these parameters will get their optimal values. These parameters will get their optimal values once the loss function has got a. So essentially what you are doing is you are plotting the loss function with respect to the model coefficients, and you want to find out for what value of the model coefficient the loss function is having a minimum value. So you will be literally having 984,000 parameters which will be minimized simultaneously. Sorry, optimized simultaneously by minimizing the loss function. Once again, I repeat, you are trying to minimize the loss function so that you can find out, you want to minimize the loss function so that you can find out the optimal value of the model coefficients. So how many coefficients you have or how many model parameters you have? 984,000 parameters. Okay. So we'll not get into the calculation how this number came and all. Limited scope for this session because of the time. Okay. But this is essentially what is going to happen. Okay. When you minimize this loss function, you will get the optimal values of how many parameters? 984,000 parameters. And that is why the deep learning model training will take huge amount of time. Now, who finds the minimum value? That is where the optimizer algorithm comes into picture. So which optimizer algorithm I'm using right now? Adam. What are the other options? Here are the other options. You can use Adam, you can use stochastic gradient descent, RMS prop, and then you have ADA delta, ADA grad, ADA max, NADM, that is Nesterov accelerated gradient with momentum and so on. So you have all these. So these are the possible optimizers. Right now I'm using Adam. Fine. So optimizers done. The next thing that I am using is the metrics. So how am I going to judge the performance of my model? Okay. That is where the metrics come into picture. Okay. Yeah. That is where the metrics come into consideration. So you can use F1 score here. You can use MSE, mean square error, for a regression problem. You can use MSE here. Okay. So what are the metrics available? Again, the same. These are the metrics. So you can use MSE, as I said. Okay. Or for classification, you can use precision, recall, ROC, AUC score, F1, and all that. Okay. So right now I'm using a simple accuracy. Fine. So you can see all the metrics available from this page. Fine. Activation functions. Yes. So all the activations which are available, can you see? I have used ReLU. Okay. But apart from ReLU, you can see there is something called a soft plus. And then you have softmax, you have sigmoid, you have many others. You have ReLU. I mean, this is the most commonly used and the default. Okay. So don't experiment. Don't waste time in experimenting. I'll tell you very, very frankly, that has already been done and tested. Okay. So people in the last 15, 20 years, they have done enough experimentations and they have shared their findings. Their findings are for the hidden layer. Once again, listen to me very carefully. Don't waste time in unnecessarily experimenting unless you want to become a deep learning researcher. And unless you have a strong reason not to use ReLU, use ReLU. It is as simple as that. Okay? Because people in the last 20, 25 years have done enough experimentations, and unanimously everyone agrees that ReLU is the best. And that was, invented in 2015 by this group, Jeffrey Hinton. And before that, deep learning was still, struggling to make its presence felt. Okay, that was the main reason. And after this ReLU came, after this ReLU was proposed in 2015, the entire deep learning landscape changed, because now the model training was so quick, so fast, not only quick and fast, but the performance also increased manifold times. So that is the achievement, I would say, that I'm taking the entire scientific community. Okay, we achieved when we are figuring out that, okay, let's use value. So that's what. So unless you have a strong reason not to use value, use value. It is as simple. Now this will depend on, so if you are solving a classification problem with binary classification and a single neuron, use sigmoid. If you want to have 2 neurons, then you go for softmax. If you have 5 neurons, go for softmax and so on. So if you have any number more than 1, go for softmax. It is as simple as that. But if you are solving a regression problem, then go for probably linear or even ReLU. So if you do not want any negative numbers, then you can use ReLU here. But if you think that negative numbers are also acceptable, use linear attribution, right? That is how it goes. And then I'm just saving this model into a PNG file, which I'm going to print it later. This custom function is for doing cross-validation kind of thing, because deep learning models cannot be cross-validated by using the SciPy package cross-validate function, because deep learning models are not upfront compatible with the scikit-learn API. So this is a simple hack. Okay, training and testing it 5 times. Okay, now here this tokenizer is same as your count vectorizer. Okay, this is doing the same job as your count vectorizer, right? So your tokenizer has this function called as text to matrix. This is the function which will convert your tweets into a matrix of numbers. Can you see? The input is your training docs, which is a list of tweets. This is a list of tweets. And you have 4 or 5 modes, I think. You have 5 modes. One is the binary mode, where these numbers will be either 0 or 1. Can you see? These numbers will be 0 or 1. 1 means a particular word from the vocabulary is present in your document. Binary mode. Then there is a count mode also. So let me show you. There's a count mode, there is a TF-IDF mode, okay, and there is a frequency mode also, okay. Yeah, so these are the 4 modes available: binary, count, TF-IDF, and frequency, right? So binary is what right now I'm using. You can go for count mode, which is going to give the exactly same output as a count vectorizer. This is going to give you the same output as a TF-IDF vectorizer. The only difference is I'm using TensorFlow functions for achieving the same thing. So essentially what I am doing is creating a bag of words model and using standard neural network to learn the pattern. The feature extraction is done by a bag of words model. Yes, feature extraction is being done by a bag of words model, which is as simple as a count vectorizer or a TF-IDF. But I'm not using the scikit-learn API functions. I'm using the TensorFlow. That's the only difference. Perfect. So you can change and experiment. So why binary? I'm not claiming this is the best. You experiment. Okay, so I've got 15,351 unique words, each word being counted as a feature. So I've got 15,351 features. Okay, good. What else? Then I have trained my model. Sorry, did a test range split. I think that is pretty logical. And then I am just creating my model. Okay, I'm just creating my model here. Yeah. So if you want to see these numbers, basically, how many input nodes you have? You have 64 input, 15,351 input nodes. So how many connections do you have in the first layer? So these many input nodes times 64. That is the number of connections you have. Plus 64, because each of the neurons in the first hidden layer will also have a bias down, right? Now you see that this number exactly matches this number. Okay, so have a look at this number. That's what this is how the calculation comes out. Okay, once again I repeat. So what is happening is you have the input nodes. So the green ones are representing 15,351 51 input nodes. Now I'm going to use the blue. So these are my neurons. So how many? 64 neurons you have. And now you have connections of each neuron in the hidden layer with all the neurons of your input layer. So how many such connections will you have? So you will have 15,351 times 64. That many number of connections you will have. So each connection has got a weight. Please remember. Yeah. So each connection has got a weight. So this weight matrix comes out to be 15,351 cross 15,351 cross 64. This is our weight matrix. This is our weight matrix. Plus 64 again. Why this 64 come up again? Because each of these neurons have a bias term. Each of these neurons have a bias term. So how many bias terms would be there? There would be 64 bias terms. So total 64 biases and these many weights would be learned. That's how you get 982,000 features. Sorry. 982,000 parameters, not features, parameters. Okay. So bias, again, so people who have some background about neural network, they know what are weights and biases. So we'll not get into all that discussion. Just like in a linear regression model, you have model coefficient and the intercept term. Think it that way. Okay. So each of these neurons will have a coefficient, which are these parameters. And each of those neurons on the hidden layer, they have the bias terms, which is like an intercept. So since there are 64 neurons, there are 64 intercepts. So intercept is similar to your bias. Okay. Now in the next layer, okay, how many connections you have? So you have 64 connections from your, so initially, let me make that once again. So this is my 15,351. This is 64. This is 64. And now in the next layer, I will have 32, right? The next layer I've got 32. So how many connections you will have? 64 times 32. And each of these will also have a bias term. Each of these will also have a bias term. Okay. So how many parameters you will get now? Okay. Let me just calculate that for you. So 64 times 32 plus 32. Okay. Perfect. Do you see this number? Do you see this number? Awesome. So this number is exactly 2080, which is 2080 here. Okay. So that is basically corresponding to each of the neurons of this layer being connected to each of the neuron of this layer, the next layer basically. And for each of those connections, you have one parameter defined. Okay. Plus 32 additional parameters for the bias terms. So there are 32 neurons in the second hidden layer. So 32 bias terms would be defined. Okay. When I add these two, what I get is, yeah, 2080. I think that is very clear. And in the last output layer, so this is my last output layer. So how many connections you will have? How many connections you will have? 32 times one connection. And plus there is a bias for the output also. So plus 1. So 32 into 1, that many number of connections plus 1. And that is the reason it is 33. Is that very clear to everyone now? Right? That's how you get 33. 32 into 1 plus 1. Perfect. Okay. So I'm still trying to be, as brief as possible because I'm expecting some, because I told you very clearly, this is an advanced level session. Okay. Some basics of neural network would be really helpful. So now when I add all these parameters, so these many parameters would be learned when I train this deep learning model. You are training how many parameters? 984,000 parameters. That is why you would need a GPU probably. Okay. So I'm not going to do that right away. Okay. But yes, that will take a lot of time if you are running on a CPU. Okay. So I just, I'm displaying the same model. This is your deep learning model in a graphical way or in a sequential way. The next thing is, I want to fit the model. But before I fit the model, in the last step, can you see I have created something called as callback. So this is something. So there is something called as callback function. Okay. So what is that callback? So callback is basically used. These are callbacks are used to do model checkpointing. What is model checkpointing? So basically think it this way. That was set up. Okay, so think this way, that let's say I'm going to train this model for 25 epochs, 25 generations of epochs. And let's say the 12th epoch gave me the best model. And after that, overfitting started. Okay. So when the overfitting starts, the accuracy of the validation split will start decreasing. So what am I monitoring? I am monitoring the validation loss. That validation loss will be minimum. That validation loss will be minimum for the best model. Okay. That validation loss will be minimum for the best model. So I want to save that model from middle. I don't want the model in the end after the 25th iteration, because quite possible the model in the end of 25th iteration might be overfitted, right? How do you know? I'll show you the plots. So if the 12th model had the lowest validation loss, that 12th model will be saved in your hard disk. That will be saved in your hard disk by this name, Okay, so that you can retrieve that model later on and actually use that. Okay, so that is the whole purpose. So you run this code and you will get to see the validation loss, training loss, accuracy, and everything. I'm just going to plot that. Okay, I'm just going to plot all that. Okay, so this is my loss function value with respect to the number of epochs, 25 epochs, and you can see somewhere that both of them decrease till this point, and after that, the gap here, you can see the gap increases. This gap increasing clearly indicates overfitting. So probably your best model would have been somewhere in this range. This increasing gap clearly tells you that your model is overfitting. Once again, I repeat, when does the gap increase? The gap increases when your model is learning better and better in the training data set, but its performance in the test set is becoming poorer and poorer. So then the gap will start increasing. And that's exactly what an overfitted model would be. Make sense? You can very well see this from your accuracy plot also. You can see the maximum accuracy was already obtained. The maximum accuracy was already obtained somewhere here. And beyond that, it's all flat. So this is a validation accuracy. So somewhere where this gap is minimum, okay, either you can freeze it here or you can freeze it somewhere here. So I would freeze my model somewhere here. I would freeze my model somewhere here, because beyond that point, there is no more increase in the validation accuracy. Beyond that point, there is no more increase in the validation accuracy. Whereas the training accuracy will keep increasing, and that is quite obvious. No, model will keep learning better and better, and its performance in the same training set will of course keep increasing, because that's like a same data for the model, right? So the performance is definitely expected to be higher on a same data. That is pretty common sense, right? Okay. So I had saved my test split somewhere. So let me get the performance. It is like 86.9% accurate on my test set, which is pretty good. 87%. You see, I'm getting 87% performance. That's absolutely good. Now, if you want to do a 5-fold cross validation, it's not exactly 5-fold cross validation, but model training and testing 5 times. So that custom function I had written to train and test the model 5 times so that I can get the variance of the scores also. That kind of gives me a hint about the precision of this model, right? So I did that 5 times, and each time you can see the accuracies are slightly different. So in the 5th time, it came out to be 89%. In the sometime it came to be 89, again 88%, 88%. So you can see that there are some differences. Anyway, perfect. So the last thing is, I'll take another 5-10 minutes. Okay, not more than that. Okay. A deployment. Now, I don't think I'll be able to cover the deployment. Maybe we'll take one more session only on the deployment. If you guys, allow me that way, or if you guys agree, so please put a request to the moderator or drop a mail to the DataHour@analyticsvidya.com. Put requests, okay, that you want a model deployment session. We'll take 1.5 hour model deployment session on AWS. I'll show you how to deploy the same model. So I'll not spend a single minute in discussing how to create the model. Well, straight away go to the deployment then. Okay, part 4. Okay, maybe I'll have to discuss whether we'll call it as part 4 or anything else. But because deployment itself will take some time. Initially, I thought I'll be able to cover it, but then because I saw that a lot of new people are coming in each of these sessions, some revision became mandatory, and that because of these revisions, easily 25, 30, 40 minutes are eaten up. So I had figured out that I'll not be able to cover the deployment anyway. A deployment will take time. So I want you guys to do the deployment along with me. Okay, so that will be more of a hands-on session. Okay, but let me plan it sometime later. Okay, so before I end the session, another last 5-7 minutes. This time what I want to do is I want to create the word embeddings, not by using word2vec, not by using glove. Okay, I'm not going to use any of those pre-trained models or pre-trained architectures. Okay, I will create my word embeddings right using a neural network that I want. Okay, so let me show you where am I doing that. So here you can use an embedding layer. Okay, the vocabulary size you have to mention 300. What is this vocabulary size? 15,000 something. Okay, 15,351. That is the number, right? Then what is the 300? So 300 is the dimensionality of the word vectors. Okay, this is the dimensionality of your word vector. And what is this max length? So somewhere here I have printed the max length. So max length is the maximum number of words in a given tweet. So out of that 7,920 tweets, the maximum number of words in a given tweet came out to be 37. So that is the max length. Okay. So these are the 3 inputs. I have already documented that here just below. Okay. These are the 3 inputs you will need. The size of the vocabulary is your output dimension. So size of the vocabulary means how many unique words are present in your vocabulary. That vocabulary you will have to pass. So your input will be that vocabulary. Okay. And then, of course, the size of the embedding and the maximum length of the input sequence. That's it. And then you have the standard convolutional layer. I am using a one-dimensional convolution because this is a text, not an image. For images, you would be using 2-dimensional convolution, or for color images, you would be using a 3-dimensional convolution. Okay. Once again, I repeat, for textual data, we use 1D convolution layer, 1-dimensional max pooling layer. For images, you would be using 2-dimensional convolution and 2-dimensional pooling. Those are black and white images or grayscale images. But if you have a RGB image, a color image, okay, then you would be using 3-dimensional convolution layer and 3-dimensional max pooling layers. Even the filter dimensions will be mentioned in that way. Okay. Okay. So this is the layer which will create the word embeddings. It is as simple as. Now, once I get the word embedding, someone has to extract features out of it, right? Word embeddings are themselves not features. They are just the numeric representation of the words. Once again, word embeddings are just the numeric representation of the words. They essentially are still not the features. So someone has to still do a feature extraction. So who will do that feature extraction? The convolutional layer. And then what is the job of the pooling layer? Okay. So in the convolution layer, you are using filters. So the filters are used to extract the features. So the output of the convolutional layer is called as feature map. Right? So the output is called as the feature map. Kernel size. So this is the size of your filter. Okay. So for a 1-dimensional filter, it is 3. For a 2-dimensional filter, this would be 3,3. And for a 3-dimensional filter, this will be 3,3,3 kind of. Okay. So that is how you will be specifying. And again, you will use some activation function for each of the layers. Okay. You would not be using activation function for max pooling. So what is the job of the max pooling? So in the convolution layer, you have extracted the features from the embeddings. But there has to be someone who will concentrate the features. So the convolution layer will extract n number of features. Okay, 64 filters means 64 features, but all the features may not be helpful. Once again, I repeat, it is extracting 64 features from your embeddings, but all those 64 features may not be helpful. So the job of the max pooling layer is to concentrate. So pool size 2 means the output dimension of the pooling would be half of this. So essentially what I'm trying to say is the output of the convolutional layer will be downsized by literally half, by downsized by half. How does it downsize? By concentrating the features. So right now you have that many features and it will be downsized to these many features. That is the job of the max pooling. Okay? That concentrates. Concentration is done by focusing on the important values in those features. Okay. Now there are max pooling, different average pooling is there. Okay. So max pooling, average pooling, global average pooling, a number of pooling layers are also there. So we'll not get into all that discussion. So once again, from those concentrated feature maps, so output of the convolution layer is a feature map. That feature map is concentrated by a max pooling layer. That output is further fed to another convolutional layer for another level of feature extraction. So you are extracting features from a concentrated feature map, right? So you are again extracting 64 features from a concentrated feature map and then further concentrating it. So it's like every deeper you are going down, the features are getting better and better. So here, just imagine that you are making combinations of the previously learned features. Okay, so you are extracting crude features from here, very crude features, raw features. Now those features are getting more fine-tuned, more polished in the next level. Now, once all the feature extraction is done, concentration is done, please convert everything into one single column. That's the job of the featuring, flattening layer. And then the job of these two dense layer is to learn the extracted features. So all the feature extraction concentration is done here, but who is learning the pattern? The pattern learning is happening by these two dense layers. Okay, and once the pattern has been learned, the control will go to the output layer. That is common sense, right? And then these are just the same thing. Okay, so here when I run that, this is the kind of network I have created. Okay, so embedding input layer, and then this is the size of, this is the output of the embedding layer. So this is the input to the embedding layer. Okay, so please understand, this is the input to the embedding layer. This is the output of the embedding layer. This is the output of the convolutional layer. Okay, so this goes as the input, and this is the output of the first convolutional layer. And then this is the input of the convolutional layer. And can you see there is a downsize happening? 30 became 15. That's what I said. 30 became 15. Half, right? That is the concentration I was talking about. The same thing is happening once again. Okay. So and then this is 15. Flattening. So 15 into 64 is 960 anyway. 15 into 64 is anyway 960. And that 960 is connected to 64. So how many parameters you will get? 960 times 64 plus 64. That many number of parameters you will get in this layer. And then 64 is connected to 1. So you'll get 65 parameters. That is 64 into 1 plus 1 of the output layer, right? So you can see those calculations in this table here. Yeah. So it is all there. So I'll just run this once again. Okay. And this part, model 2. Yeah. So yes, so that's what I was wondering. Where did the other convolution and pooling go? Yes, so we have got 2 times convolution and 2 times pooling. So this is the first convolution pooling. This is the second convolution pooling. So 17 goes as the input for the next convolution. And again, that is roughly reduced by half. Can you see 10 by 5, 10 to 5, 10 to 5. Now this reduction is happening because of the filters. This reduction is happening because of the filter. And there is a padding, stride, and all that concept. We'll not discuss all that, but this reduction is because of your stride and padding. Okay. Whereas this reduction is because of the pooling size of 2. Okay. So 10 is reduced to 5. And now that is 5 into 64. Finally, you have those numbers. Fine. So just run this code. This will take some time because 25 epochs, and then you will get the. So here in this case, something interesting I've got. I did not get a very good accuracy as of now. So maybe I would encourage you to experiment with some of the model parameters and see what is happening. So I did not get a very good accuracy. Probably this is overfitted. I guess so. And I'll tell you the reason why I'm guessing it to be overfitted. This is very, very highly overfitted. Okay. Now we will need to control that overfitting. How can I claim that this is overfitting? Can you see this? Accuracy is 99.99. So this is a training accuracy. This is a training accuracy, whereas validation accuracy is 68%. So that hints overfitted model. So you will have to put some good amount of regularization, and probably then the performance will increase. Okay, so how do you put regularization? Here regularization was missed out, right? So let me just copy that regularization part from here and see if that works. Kernel regularizer, and then also a dropout. So let's use the dropout also. So somewhere you will paste somewhere. So you will be using this. And then you want to use a dropout layer. So normally you use a dropout between the dense layer. That's what I told you there, right? So don't use it anywhere else. Between convolution and pooling, you can use normalization, batch normalization. That is another concept of reducing or controlling overfitting. Okay, batch normalization. Okay, if you go to the normalization layers, so this is what I'm talking about, batch normalization layers. Okay, so that is what you should be using ideally between convolution pooling or between one batch of convolution and pooling. So this is where you can use that normalization layer. Okay, so this is, I think, good enough. Let me try this one last time. How does it come out? Let's see. It still is overfitted. You can see 97 already reached, whereas this is struggling at 66, 67%. So maybe we can further, put some, let me try with L1 regularization or increase the regularization term. Okay. So now that is your task. I mean, okay. Just stop that process. And that is stopped. Let me try that once again. 74, 72. Now this is doing good, but I fear this time it might be underfitted. So both are 74, 72. Can you see 74, 72, 74, 72, and it's not increasing. So L2 is not working and L1 is very brutally working. Okay, but at least this is better. So you'll have to, tune the regularization parameter there. Okay, regularization parameter. So you can see this has improved and this is not overfitted like before. You can very well see. And how do you know? You can see this 74 and 72. This is definitely not overfitted. You can also copy that previous code for plotting and do a plotting also. So maybe if you want, I can just copy this and finally show you the output. Okay. So I forgot to save the history here. So H1, let's call it as. So unless you are saving the history, can you see, you'll not be able to retrieve it. So let me just try it once again. And then from there, We have to change these parameters. See, this is the number of parameters is huge. It's 1.7 million parameters. Since I'm using the GPU, it is training extremely fast. Okay. The GPU that I'm using is 32 GB GPU with 7 cores. Titan RTX 5000 is the GPU that I'm using. Okay. So don't try this unless you have access to okay. Okay, so you can see that is very much controlled, but this is underfitted. I would say this is underfitted because you can easily get an accuracy of, and this gap is not huge. This is a very small gap, although you can see this plot is not coming from 0. This plot is coming from 73% already. So this gap is not huge. Don't think that this gap is huge. Okay, if I just put a plt.x label, sorry, x lim, show you between 0 and 1. You see, that's what. Sorry, lim, not x lim, lim. You can see that this is very much for point. The difference is not huge actually. Okay. Fine. So let me stop here and see if there are questions and comments. Okay. I have already taken 20 more minutes.
So before we proceed to answer the questions, I would like to request the attendees to please fill in the feedback poll as it helps us to conduct more such sessions.
Okay, I'm just in the meantime reviewing the chats. Ayush is asking, where can I find deep learning and data analytics enough to understand and train models? Okay, so on Analytics Vidya, if you go to courses.analyticsvidya.com, there are 3 free courses on deep learning. Let me tell you, 3 free courses. One is Fundamentals of Deep Learning. Second is there is one course only on neural networks also. Sorry, convolutional neural networks. Okay, and there is one more course on NLP with deep learning. So there are 3 courses, and those are 3 free courses. So you can just check out that. Okay. So courses.analyticsvidya.com. There are 3 free courses on deep learning, and one has convolutional neural networks with deep learning. I mean, so Edward, thank you. Thank you for the praise. Thank you, Adarsh. Mayank, I understand your concern, so maybe we'll take the deployment in the next part. Okay. Francis, okay, you are new to deep learning, but still you found it to be interesting. Okay, thank you. Yes, deployment itself is a complete different ball game. I mean, so that I thought let's not put too many things. It will be a complete khichdi, I would say. So let's keep the deployment. I'm sorry that I'm not keeping up my promise for this session, but definitely once we have that deployment session, you will like it even more. Okay, so that becomes from end to end. From scratch, we did data cleaning. You see, every single thing we have done. We have done all the bag of words model, all the neural network model, all the embeddings, everything. And then when you are able to deploy it, I mean, that's what you call as a end-to-end data science project worth putting in your CV, right? So perfect. Thank you. What else? So I've already shared the GitHub link just in case you missed out. Let me post it once again. Thank you, Sumit. Thank you, George. I have posted the GitHub link where you can download all these codes. Everything is there. Okay. Okay, and where is the Q&A? Okay. Lokesh is asking analysis of readability. What is format? that is out of context. Frankly, I would recommend you to ask ChatGPT. That will give you a better answer. Okay, that's completely out of context. So I'll not get into that because the session is already staged. Sandeep is asking, can we apply NLP pre-processing again for identification of sentiments after deep learning? Apply NLP process again, pre-processing. See, pre-processing is always done to make sure your data set is neat and clean, of course, and in the right format as the algorithm is expecting. A ML algorithm or a deep learning architecture is expecting before it starts doing that training, right? So you would not do any NLP stuff at the time of model building. So that's the systematic flow which I have already given. Just in case you want to note it down, I'm pasting that entire flow once again in the chat box. Okay, please copy and paste it somewhere. Okay, that entire flow I have given it. So you would not be going back and forth every time. So all the pre-processing, some minor tweaking will be needed depending on what kind of model you are building, as you might have realized. Okay, so when we made a simple ANN model, our pre-processing was different, and we did a different kind of pre-processing when we were creating our own embedding layer, right? So that you will see. George is asking, are you getting the tweets from the live Twitter feed? Not yet, but you can do that. You need a Twitter developer account. Sign up for a developer account. They will give you a API token. Okay. So using that API token, you will be able to download the feeds, the Twitter feeds, by giving some keyword. So what is that keyword? Keywords will be your hashtags. So for a given hashtag and a limit, they will give you some limit, maybe 5,000, 10,000 limits. So you will be able to download that many tweets for a given hashtag or a combination of hashtags. Okay, so definitely you can do that. For that, you will need a Twitter developer account and a access token. Okay, API token. How to do that? Ask ChatGPT. Definitely, it will be able to help you. Okay, how to download data from live Twitter feed? Just paste the same question in ChatGPT. You will actually get the Python code. I've tried that. Okay. So some of your problems can be easily solved by using ChatGPT. I'll tell you very frankly. Okay. George is asking what is the benefit of branching. A very good question. Actually, I'm expecting that you're talking about the branching of the neural networks, right? So suppose you want to do Engram, right? So if you want to do Engram model building using deep learning, that is where you will do the branching. So one branch is doing the unigram token processing. The next branch is doing a bigram processing. The third branch is doing a trigram processing. And then you collect all the features from unigram, bigram, and trigram. So you collect everything, and then you start your other things like convolution, pooling, dense layers, followed by your. So that is where you can actually go for branching in this particular data set itself, in this particular project itself. So branching, definitely. I had that code somewhere. Maybe I can share my screen, but it's not there in any of these notebooks. Let me see if I can show you. I had that. No, sorry, not here. So you will be using that branching somewhere. Not here also. Somewhere I have that. Maybe. That's okay. Fine. Another question is AFINN model. What is this AFINN? Artificial fuzzy inference neural network. Is that what you are asking? So we have used these models, right? So one more enhancement that I would probably suggest from here is maybe you can try LSTM after the output of the CNN. Okay, so even that you can check. The advantage of LSTM is, or you can replace the CNN with LSTM. So you have the word embeddings, and then immediately you can put the LSTM layer. The advantage of that LSTM is it will be able to capture the sequence of the words. So right now, what you have created is essentially a bag of words model. And from that bag of words, you have extracted the features by using convolutional layers, concentrated the features by using pooling layers, and then learned the features by using dense layers. That is what you have done. What you could have tried also is get the word embeddings or get some numeric representation of your words. And those numbers can be fed in sequence. So LSTMs or RNNs, recurrent neural networks, are excellent architectures when you want to use it for sequential learning. So these words come in sequences, right? There is a sequence of words in a paragraph, in a sentence, so that it makes an overall sense and a context, right? So when you are feeding the words to a network in a sequence, that sequence is completely lost as of now. Whatever model architecture we have trained today, there is no sequencing in the words, right? So when you are feeding those words with their right sequences to a LSTM layer, okay, you might get a better performance. Okay, so you just have to try that out. I haven't done it as of now in this particular project, but definitely that is worth trying. Okay, that's one more enhancement. You can do that. Okay. Thank you all.
Thanks a lot, Prashant sir. On behalf of Analytics Vidya, I would like to thank you for your time and delivering such sessions. I'm sure audience found it insightful, and hopefully we can conduct more such sessions with you in future. I hope you guys have filled in the feedback poll. If not, I request you to please fill it, as it helps us to conduct more such sessions. We will be back with another session of DataHour on 18th of January, and the link is in the chat sections. Till then, bye bye and keep learning.